Okay, so what we are going to do here is look at the overview of organic chemistry here for this metabolism course. So what I want you to know here for this group of lectures are the families of organic compounds. So you should be able to name simple compounds and identify functional groups on them. So these are all things that we have previously done in organic chemistry. And so I'd like you to be up to date with that. Understand the properties of these families, organic compounds. So what are their physical properties, their boiling points, their reactivities, and what forces explain these properties. Also understand which of these families of compounds undergo which kinds of reactions. So this is what we're going to cover in this set of lectures, and this is what the first few chapters that are in the syllabus are covered. So I think the big thing here that we want to think about is that essentially 95, 97% of our bodies are made up of these six elements here: hydrogen, carbon, nitrogen, oxygen, phosphorus, and sulfur. A majority of what our bodies are made up of. Different combinations of these components make up proteins. They make up carbohydrates. They make up lipids, as well as some of the vitamins and minerals that we use in our bodies. So this is kind of our biochemistry periodic table of elements. And what you'll notice here, one of the things that that we look at in terms of the importance of these are the unpaired electrons and how that changes how they interact with other things. So you'll notice on the bottom here we have hydrogen. Hydrogen is only going to make generally one other bond with it because it's got this lone pair electron here. So we might bond another hydrogen to it, for example. But we basically are going to be looking at the number of lone pair of electrons here. So oxygen has 2, so it will typically be able to make 2 interacting bonds and, for example, make water. To fill that octet up, nitrogen has 3, so generally will make 3 bonds, and carbon will have 4, and generally will make 4 different bonds to fill out the octet. Obviously, with hydrogen is a little unique because it just is in that s orbital. If you go all the way back to Gen Chem, think about the s and p orbitals. Remember, the s orbital only has spots for 2 electrons, where we have an s orbital for oxygen, nitrogen, and carbon, as well as 3 p orbitals, so there are a total of 8 electrons that can fit in there. We can show this in multiple different ways. We can show with the Lewis dot structure, where the dots in between the atoms, that they're actually technically sharing these electrons. We can also say that there are lines here, and we can also condense that formula and just kind of say CH3. These are all different ways that we can show that we have molecular bonding events occurring. So what I want you to do is think about right here, what is the condensed structural formula of this compound here? What is the molecular formula and what is its name? And the goal here is to think about what are the differences between these naming systems. So if I say structural formula, molecular formula, what's its name? These are all things that you should be able to kind of differentiate between. So I would pause right now, try to answer the question before you just move on to the next section. All right, so hopefully you've unpaused it. You've actually thought about this before just going on. And so the condensed structural formula is actually listed here below. So this is just where we've basically taken these bonds out and listed the groupings of components together in one group. So we have the CH3 that represents this carbon and these 3 hydrogens. Then we have a CH2 group that represents this bunch, and then another CH2 group, and finally another CH3 group on the end. So this still kind of gives us some information about how these things are organized within each other, but it's still more of a condensed structural formula because we still have some idea about the structure. The molecular formula, we really don't know much about the structure anymore. We just know it's a molecule, and there are 4 carbons in that molecule and 10 hydrogens, but we don't really know how they're arranged within between each other. And in terms of its name, we'll talk about this in a second, but methyl, ethyl, propyl, butyl, there's 4 of these. They're all single bonds, so it's going to be named butane. So this is a list of the families of organic molecules. Alkanes, alkenes, alkynes, they're all just hydrocarbons with different numbers of bonds. So alkanes have single bonds, alkenes have double, alkynes have the triple bonds. So the big thing is when we're naming these things, at the end of the name, we're going to have the ANE, ENE, or YNE endings that dictate how many single, double, triple bonds there might be. Aromatic compounds here are shown. We'll talk about that briefly as well, but aromatic are compounds that are cyclic and then also have these every other carbon has a double bond, and again that makes it aromatic because we can have those lone pairs of electrons kind of flowing around in that aromatic system. Alkyl halides have halogens, those components on the periodic table next to the noble gases, fluorine, chlorine, bromine, iodine, for example. And we usually don't use ending names. We usually use prefixes for these compounds. Alcohols is another functional group that is important, is the OH group, and generally that'll have the OL ending. Ethers have this oxygen in the middle of 2 carbons, and then amine groups have just that nitrogen based. We'll usually add the amine ending as well. Aldehyde, that is where we have this carbonyl group at the end of a chain. Ketone is a carbonyl group within a chain, and notice the difference there. The aldehydes have the al ending, and the ketones have the on ending. Carboxylic acids, we have that carbonyl group as well as this extra alcohol group, and we add the ic acid ending to carboxylic acids, for example acetic acid. And hydrides, this is where we have basically 2 carbonyl groups and an oxygen in the middle. Esters, we have basically this carbonyl group, oxygen, and this carbon chain continuation. An amide functional group, which is found in proteins, is that carbonyl group with the amine group attached. We have the amide ending. So those are some of the more important functional groups that we'll talk about. We're going to kind of walk through each of these and how they're all different, and some examples of why they're important. So we're going to start with some of the hydrocarbons, where we only have the ANE starting with single bonds. The alkanes here, we have just the single bonded carbons. Just to review the naming systems: methyl, ethyl, propyl, butyl, pentyl, hexyl, heptyl, octyl, nona, deca. The name is reflective of the number of carbons in the longest chain of any compound. I'm not going to cover naming or nomenclature, but if you have an interest, here's a link to that kind of information. Even though naming is important and it allows chemists and biochemists to look at the different types of compounds and agree on names, the problem is that biochemists have long been using chemicals that they didn't know what they necessarily looked like, so they had names before IUPAC came along and created a standardized system. It gets a little cumbersome, for example, if we're looking at this compound with stereochemistry and we have to name these things differently. This is the compound glucose, so it's a simple carbohydrate, glucose. IUPAC naming system would be 2R, 3S, 4R, 5R, 2, 3, 4, 5, 6, pentahydroxyhexanol, right? So it gets complicated. There's the AL ending, which suggests it's an aldehyde functional group, multiple hydroxyl functional groups on here, so that's what the 2, 3, 4 hydroxy part is. So that is how we would name this compound, but in biochemistry a lot of times we're not going to be using IUPAC. So Just to go back with, so we've kind of talked about the naming systems, and here is just some of the properties of alkanes. They're generally not going to react with acids, bases. They're very nonpolar, non-toxic. They can be flammable. That's one of the things that can happen with them. So they're good combustion agents. We use these things in our cars to break apart these energy bonds. So a chemical reaction that produces a flame usually becomes it's burning with oxygen. So carbon dioxide and water are products of complete combustion, and heat or energy is released during that process. So when we light something on fire, right, that is combusting, that basically carbon dioxide is being created on that combustion. When it happens in our bodies, right, we still release some heat energy. We harness that energy in different ways in our body, but we still breathe out carbon dioxide and water.
Combustion is really also a redox reaction, which means a reduction and oxidation reaction. And ultimately, when we're looking at a reduction, we need to think of this as a gain of electrons. So electrons are coming closer to the nucleus of a certain atom. And an oxidation reaction is a loss of electrons. We're usually talking about carbon being oxidized or reduced in organic chemistry and or in biochemistry. And what happens is when we have a combustion, right, we release a lot of heat. In biochemistry, we don't just release heat, we actually create different compounds that have a capacity to have higher energy. So here is a more oxidized carbon. Right here you can see that it has more oxygen to carbon bonds on the left side, and here on the right side that oxygen has been now reduced, or this carbon, has been reduced. We have less bonds to it. There's only a single bond from this carbon to that oxygen versus over here there's a double bond here. So this is an important chemical reaction in biochemistry because it's a way that we can harness energy through these other NADH molecules, which we'll talk about later in the semester. But not a lot of chemistry that is really complicated, but it's an important part of the energetics of our systems.
Alkenes and alkynes, another type of hydrocarbon. Naming alkenes and alkynes, we have different ways. Name a pentene, for example, 5-carbon chain. Right now we're adding that ene ending. The triple bond, we add the YNE ending. So we generally are going to keep, even if we have, for example, 1, 2, 3, 4, 5, 6, 7, a 7-chain ring versus a 6-chain ring, we're going to keep that double bond in that longest chain should incorporate that double bond generally. Just something that's typically done. So like alkanes versus alkenes and alkynes, they're very similar. They're nonpolar, insoluble in water. They are flammable, but generally non-toxic. So there are no functional groups to really have a function on anything. So they are pretty non-reactive. There are differences with alkenes and alkynes in terms of their isomerism. So we can have cis and trans isomers because they have double bonds. So those compounds can fold off of those chains differently and form different structures. They are chemically a little more reactive at that double bond than a typical alkane. So if we have, for example, one of the properties of carbon chains is the longer they get, the more temporary induced dipole-dipole interactions there are, or intermolecular. This is an important intermolecular force. So we talked about this in the past, where we have these forces and we have these electrons that are in these carbons and these hydrogens, and they kind of flow back and forth. Electrons kind of move around in these spaces a little bit, and that creates this kind of positive and negative charge difference, and they can kind of get the longer the chain, the more of this can happen. And as you see here in this figure, this is the number of carbons associated with that chain. As we increase to the right, you'll notice that the temperature for the melting point and the boiling point both continue to increase. And that's a result of those London dispersion forces, van der Waals, or the temporary induced dipole-dipole. All the same kind of idea, same intermolecular force with just a different name. So those are kind of the properties of just hydrocarbons alone. Obviously, sorry to go back to this, but the melting point and boiling point, we looked at this. We've discussed this previously in other classes, but that can change based on if you have differences in cis fats or trans fats, right? We have those double bonds changing the structure. That can interfere with the laying down of those carbon chains on each other, and the interaction, the intermolecular forces can then. One of the questions I have here is what happens when we add hydroxyl groups or OH groups onto these. So you should think about that. That should be something you have a firm understanding of what happens there. I'm not going to talk about it right now, but again, that's something you should be aware of. What's that functional group going to do to the melting points and boiling points?